Welcome everyone. Thank you all for coming, and I'll hand over to Cameron now to begin his talk.
Thanks. Um, we were talking about one of my favorite papers, Deep Reinforcement Learning That Matters, that tries to bring up some of the issues with current approaches to evaluation in the field of reinforcement learning, and especially concerning deep architectures. So we're going to spend time going over this paper, talk about key points from some of the related papers, and then go over into a discussion about potential ways we could try to remedy those issues. Cool. So diving into the paper straight up, I'm very quickly going to try to define reinforcement learning. Reinforcement learning is the machine learning problem in which we're trying to learn a behavior or also known as a policy of an agent in a particular environment. This is very often done in a way that's trying to maximize some measure of utility, also called as a reward for that agent in that environment. Classical example is trying to balance a pole vertically, where the reward is the amount of time that the pole has been kept upright, and where the possible actions of the agent is like sort of moving a cat underneath the pole, so that you can try to adjust the pole if it ever starts to lean in a certain direction. And yeah, as I said before, DeepRL is doing that with deep neural network architectures, which take as input the state of the world and try to output an action that tries to increase the reward of the agent. Cool. So this paper opens with the sort of like mentioning the increased interest in reinforcement learning and the seemingly very impressive achievements that it's been able to do. Like it's really taken the world by storm in some of its things that it can do, such as being able to play Go better than any human can, and more recently being able to play complex strategic real-time strategies such as StarCraft 2. So the goal of the paper is to bring up, to shine a light on some of these results and try to put into question whether they are as impressive as they may seem, just like at face value. And the way it does that is by looking at some of these at four, I think, particular learning algorithms called Trust Region Policy Optimization, TRPO, Deep Deterministic Policy Gradient, DDPG, Proximal Policy Optimization, PPO, and Actor Critic using Kronecker Factor Trust Regions, ACTOR, which were at the time of publishing of this paper, the state of the art. And then what the authors of this paper start doing is they start to ask questions about like the robustness of these algorithms when some of the particular choices that were made while training them are up for changing. And the first question they ask is, as with any deep architecture, we have some hyperparameters. How robust are these algorithms to different hyperparameter settings? And I think, unsurprisingly for most people who deal with machine learning, is they find that they're not very robust to hyperparameter configurations, to changes in hyperparameter configurations, with an algorithm that can perform incredibly well, attain superhuman performance in particular tasks, not being able to do anything with a different hyperparameter configuration setting. This seems to be something that's very often the case in deep learning, and I don't think the authors consider this to be a major drawback of DeepRL, but it is something that is worth considering. The next thing they analyze is how how does the choice of network architecture for the policy and value function approximation affect performance? So the policy, as we said before, is how is the agent's behavior. So the policy of the agent is what do I do given I'm in a particular situation. The value is how good of a situation am I in. So these are often, depending on the method, we have different neural networks trying to predict what these settings are, which is a difficult problem because these agents very often operate in a setting where you don't have complete information about the world. So to sort of like draw a comparison there, in the game of Go, or chess, I have perfect information about the world because I observe absolutely everything there is about the game state. But in the game of StarCraft, I do not observe what my opponent is doing all the time. So I need to have a guess about exactly how good my current position is in the game. So they perform several experiments with several different architectures where they change the number of layers and the number of hidden units in each layer for these neural networks, where they use feed-forward neural networks or multi-layer perceptrons. And they also change the activation functions under consideration between Tanaich, ReLU, and Leaky ReLU. So going over into figure 2, they evaluate this on 3 different, actually, is it 2? No, sorry, this is on the same environment, but different algorithms. So let me zoom into this. Looking at the leftmost figure, they find that, well, okay, basically across the board, they find that for each algorithm, the architecture choice changes. So these algorithms are very much tied to the architecture that is used for their approximated networks for the policy and value states, value functions. Sorry. This is again not particularly surprising, but it's sort of like a point against the overarching thinking of, these are algorithms that can adapt to any situation. They're very much a part of a complex combination of learning algorithms, and as we can see, are not super robust to the choice of things, of everything else. Cool. So nothing incredibly surprising so far, but this is where I think we go into the more interesting thing. Is this reward I mentioned of like how well I'm doing is represented by some number, and I can try and scale my number, just multiply it by a constant, and see how my algorithms perform on the exact same task, but we just a scaled up or down version of the rewards given. What is found in this set of experiments is that by scaling down my rewards, making them a tenth of what they originally were, performance very often improves, which again sort of shows to the sort of brittleness of some of the approaches in the field, as you would expect, just doing this change of the reward that leaves reward comparison invariant, for example, shouldn't really affect the performance of the algorithms. For us humans, it doesn't matter whether I'm playing a game where I earn 3 or lose 1, or earn 0.3 or lose 0.1, if everything else is scaled accordingly as well. Now this one I think is very, very interesting. There's inherent stochasticity in both the environment in which these algorithms are deployed and in the training. So in RL, we don't necessarily operate with predefined data sets, as is the case with other machine learning, but you're giving a simulator that you can use to generate unique trajectories through your game for a lot of the tasks. This is not true everywhere, but for at least for the task considered in this paper, is true. So then the question arises of given different initializations of my learning algorithm, given different rollouts from my environment, how robust are these algorithms to these variations? And what I find is that they are not robust at all. They are quite brittle in a sense, to I'd say an absurd extent in some situations. So let me just find the relevant table. So I'm just looking for which table it was. Okay, let me try to decipher these tables. That's not good. I think, yeah, I think this is the relevant graph, where what they do is they use the exact same implementation of the same algorithm, but run 5 different studies and produce averages with error based on that, and separately do this again. And what I find is that 5 runs is nowhere near enough to produce a stable approximation of how this algorithm does overall. So this is, again, the exact same algorithm and the exact same implementation. And this last part is important, as we'll see later on. Just run 10 different tools and split into 2 batches of 5. As we can see, these seem statistically significantly different. And therefore, the error bounds provided are just provide us with a false sense of security. We feel like we wouldn't really observe something outside of this range, but we definitely can. All right, so then they move on to reviewing how algorithms do across a sweep of tasks. Again, a very large, like I think the sort of big motivating goal for reinforcement learning is trying to find an algorithm, single algorithm that can perform well across the board. And this experiment sort of tries to show that, at least with our current understanding, we don't have a algorithm that's obviously better than all others present. There's still the situation where you need to choose the correct algorithm for the task. So the environments that they look through, they have 4. These are all continuous control environments. I'm not gonna explain exactly how they work, but it's trying to, very broadly, it's trying to take some agent that you can control joins to perform a certain action. So looking at the comparison across environments, we see exactly this is for a particular environment, one of the 4 algorithms performs better, but once we change the environment, we see that another often performs better, with its DDPG winning on Cheetah, TRPO and PPO and Actor performing about the same on Hopper, and then TRPO completely blowing everybody else on Suno. Are there any questions so far?
Yes, there are some questions. So I have one. It might be a naive question. You talk about how the random seeds that they've, about the seeds having an influence on the overall performance of these algorithms that they've reported. Do you think it's coincidence that they've actually ended up with the random seed that they've used and then reported ends up being the highest in terms of their outcome, or do you think that they've like optimized this some way?
That's an incredibly good question. I think this speaking to like a larger part of, you know, proper scientific procedure in machine learning. I cannot attest to the particular papers here because I haven't reviewed them, but the possibility for, you know, this sort of manipulation is definitely there. So one of the things that you don't see with a lot of these papers is them providing implementations that you can reproduce the results that they present exactly. Right? So they, even if they provide a code that you know, produce the run that they report here, unless you're given the exact settings of all the hyperparameters that they used and the random seed, you cannot get exactly the same run, right? And let me see if we'll see this. So I think I mentioned this before, but like depending on the run, you can just have runs that completely fail, right? Runs that do not take off at all. So with that in mind, I think like I don't want to make the statement that any of these papers did this, just because I don't have the information to do so. But there is definitely the possibility for somebody to do that, and they would not be caught unless like we improve our procedures on the review side of things. Did I answer your question?
Yes, you did perfectly well, thank you. But I've got another one. This one related to the hyperparameter configuration this time. So you talked about the hyperparameter configuration having big knock-on effects on the overall performance of the algorithm. So are there any hyperparameters specific that that might have, you know, overly large perturbations on the results, or is this just a general thing?
So I would say it's more the case that for a random hyperparameter, the region in which it performs well is relatively small when you keep everything else constant. So you are more looking for a lucky coincidence of hyperparameters in deep RL, is my understanding, rather than, you know, like sort of like shooting in the dark and finding some setting that works. There's a lot of tuning of hyperparameters that happens behind the curtains that you have no clue about when you're reading the actual paper, right? So this is another source of bias is, you know, like these are still data sets in disguise, these environments, and people very often say reinforcement learning is the only place where it's okay to test on your training data, because, you know, like I'm seeing episodes like just rollouts of my simulator that are with the same settings as my training data. So this is something actually that people are advocating for, is trying to separate your train and test simulations where like you just have different distributions, right? You're trying to learn on a certain distribution over rollouts of this and trying to generalize to something that you haven't seen before. Yeah, cool.
Cool, answer my question, thank you.
If not, I'll move on. Cool.
Wait, so, sorry. I do have one more question I read down. Is there, so you've talked about these 3 algorithms, or these 4 algorithms that are typically used to train. Is there anything about these 3 or 4 algorithms that makes them uniquely brittle, or are they generally just not ready and nobody really understands why?
They're fairly complex, so there's a lot of moving parts into them. They have come as a series of additions on previous algorithms, and it is often unclear whether a particular addition contributes to the performance overall. There's this thing called an ablation study, where you try to remove particular parts of the algorithm and see whether the performance remains. when an ablation study is done on a lot of these things, is we see that each individual component is necessary for the resulting performance, but we can't really, separate how exactly it contributes to the performance of things. We see that the performance goes down, but it's not as easy as saying, if I remove component A, my agent cannot jump anymore or something. Right? It's a very complex interaction between these things. So these are all complex methods that achieve the state of the art at the time. There's actually this gives me a good point to mention this. There's quite a cool paper that says you can do a lot simpler things and still achieve competitive performance on particular tasks. So it's not like this is the only way to do these things. This is maybe arguably the easiest way, where you just throw a lot of compute to things and you get performance. Yeah, so sorry, to summarize to your question, these are not the only algorithms that exhibit this behavior. Most deep reinforcement algorithms are fairly brittle to this sort of analysis.
Thank you.
Cool. All right. So I think we managed to close this out. If there are any questions regarding this, feel free to ask. Yeah, so we move on the environments. We found that no learning algorithm out of this is better than the others on all environments. There's a really interesting point here, is that looking at these graphs, we can very easily fall into the trap of saying, ignoring TRPO. PPO seems to be better than all the others because it achieves a greater reward, right? But we still need to keep in mind that the reward is probably something that's not inherent to the problem. This is often something that we've introduced in order to be able to use these algorithms. And we need to investigate how our algorithm actually performs. So we need to see how the algorithm, what behavior it exhibits in that one. So very quickly, the swimmer environment is an environment where, as you can imagine, you need to navigate water-like environment through some joint manipulation, right? And what ideally you would like to see is for your agent to learn something like a breaststroke or something like that. A reward of 130 is achievable by curling up and flailing your entire body or the agent's entire body. And even though this behavior achieves a higher reward, this is, I think, you can reasonably argue this is not behavior that you want your agent to exhibit. So another aspect of reinforcement learning is just chasing the reward is insufficient. You can probably find settings for your agent's behavior where you achieve a higher reward, but the resulting action is the resulting policy is not something that you want for your downstream tasks. Okay, so a really interesting one is code bases. So sometimes algorithms papers don't provide implementations of their algorithms, or sometimes people try to implement the algorithm in a different language. And then the question is asked, how does the performance compare across different implementations? And this is something that I think is probably mostly exacerbated in deep learning. I think in the, in deep reinforcement learning is what I mean. In deep learning, it may still be the case, but nowhere near to this extent. This is, I think, probably the most interesting figure of the paper, is we have the same algorithm with the same hyperparameters, but different implementations of that. So using as much information as possible from the papers, trying to do your best job of replicating the results in the paper. As we can see, the resulting agents learned by these three different recommendations vary wildly. If we assume that the utility is an accurate measurement of how useful the agent is, which we saw that we shouldn't do before, is like this thing can be twice or 4 times as useful as the other implementations. So it's not even only sufficient to be as accurate as possible in what configuration you use to train your things. It's probably the only way you can remedy this issue is like by providing the exact architecture that managed to achieve this thing, which sort of speaks to the underlying sort of like unspoken goal of reinforcement learning, which is often to just find a good agent rather than find a good learning algorithm that consistently produces good agents. So yeah, I found this is a very surprising figure. Are there any questions?
Yes. Why do you think the code base might actually influence this at all? I mean, if we already have the same architecture as beforehand, the same algorithm, 2 straight implementations, I mean, I'm thinking maybe there might be something to do with, I mean, but it would still be, like numerical precision, but still that would be, and if you've got the same random seed as well. But if you've got all of those are exactly the same, why, other reasons could there be for the code base having an influence?
Mm-hmm. So that's a good question. I believe, and I'm not 100% certain, that I think these are implementations maybe in different languages or using different frameworks. So let's say, just for the sake of the argument, that this is TensorFlow and this is PyTorch. The exact same operations underneath in the framework are done differently, right? So as you mentioned, numerical precision could be done differently. We could be using, floats in one or doubles in one, or in another, or it could be more severe as something as like, sampling in one is more biased towards like a particular space of the sampling distribution as opposed to that one. I think I'm wondering about that because you have these guarantees that like particular sampling approaches will converge in infinity to the exact distribution. Well, obviously we never run things to infinity, so depending on the implementation, you will get different answers. So like we have these macro scale actions that seem the same, but have minuscule differences in the implementation underneath. And if you're, like if you're using these building blocks in a not very robust way, these minor differences actually have large effects, right? You have like a knock-on effect on things. And I think this is where these differences come from. Cool.
Great, thank you.
Yeah, thanks. That's a good question. I think. All right. So then these are all the sort of questions that get thrown at these things. And after this analysis, I'm fairly or I was fairly convinced when I saw this paper the first time that we need better ways of assessing the reinforcement learning algorithms. All of these papers are like, recognized by the community as something that has really progressed the field further. And they have, I think, quite deep flaws to them. All right, so what do the authors suggest here? I think, as I mentioned in the promo, they don't have like a clean-cut solution to things, but they start to make some suggestions. So obviously being able to do more runs of the algorithm would produce, better estimates, such that you don't hopefully see something like this. But we really have no idea how many runs are sufficient such that you don't run into this behavior. So they suggest doing sample bootstrapping, which is just very generally, I can produce confidence intervals, like saying that my true value is somewhere in a range 95 with 95% confidence by taking a lot of runs that I've had and estimating my underlying value based on subsamples of these runs. This is like a standard statistical thing to do, and we don't see it being done in RL, so it should just be adopted as a practice, right? Like this is basically for free. They also argue about sort of trying to see what's a good sample of runs to see whether like you will catch some statistically significant results, or this is just due to your small sample size, you just have been lucky or unlucky and have gotten an outlier thing. Again, a fairly standard statistical thing. And the final thing that they mention is so I'm just trying to remember. Yeah, so overall, like these 3 points is just advocating for more robust statistical testing on things. We have a lot of the tool already developed, so we can just try to map it onto these problems, which sometimes may not be super straightforward, but we can sort of begin to try to address these things. This wasn't super useful, sorry, but yeah, we can start to make strides in trying to address this. It's not like we are completely in the dark. We've just been ignoring it largely so far. Cool. So they finish by rounding out some recommendations. Is there a question?
We can go for the conclusion first.
Cool. All right. All right. So let's see. So they advocate for reporting as much as possible, because as we've seen, even missing one detail can have a major impact on somebody else being able to reproduce your results. Then they advocate for more rigorous statistical testing, and they close out with this, which I've seen echoed in different places. It seems unlikely that at least the current approach to reinforcement learning will produce an algorithm that is going to sweepingly be better than all other algorithms. Therefore, it probably makes sense to both show where your algorithm performs well and also show where your algorithm fails. As we saw before, each of these algorithms taken, has a failure condition on some of the standard benchmarks, and therefore doing this analysis can bring more confidence to the community that you've not just cherry-picked your results, you've actually done the proper analysis on the environments. Cool. All right. So question?
Yes. So in your previous section, you gave the author suggestions about you know, how they could possibly, I mean, to me, it sounded like how they could address the fact that the robustness of the algorithms is not being reported on appropriately. But if we actually, perhaps we wanted to increase the robustness of the performance overall, are there any techniques or things that you know that might do this?
So that's a good question. I think anything that I would personally suggest would probably be incorrect, just because of my lack of deep understanding in the field of RL. So I have some suggestions from people better acquainted in the field than me, and the sort of thing that they suggest is so one thing to do is definitely this training data sort of like simulator split. Is like it's becoming less acceptable to use the exact same simulator to generate both the data you train on and the data that you test on. So this split is something that can be done. Well, I want to say fairly straightforwardly, but even that has complications because how exactly do you measure the distance between the two simulators, and when do you say that something is still the same task? Like there's a gradient to that. That's unclear how to optimize exactly. Another thing to sort of measure and try to understand better is the ability of deep reinforcement learning to memorize. So things have been tried in the sort of like introducing sticky actions, making your algorithm try to do something, but with some probability just doing something completely different or doing the previous action, in the hope that this introduces this sort of like increases the envelope of what the algorithm can handle. It sort of experiences more scenarios and therefore it can do better. But it has also been shown that this is insufficient to overcome memorization or overfitting through memorization. So there's also, I don't remember exactly what this goes over, so I'm going to skip it, but there's also been other attempts of doing this, but nothing has been like super complete yet. So I think we should, one of the main things that we should do is sort of try as a community to agree on whether just very good memorization of behavior in particular situations is something that we desire, or like should these algorithms should an algorithm that perfectly memorizes everything that it's been through and can perfectly replicate a certain action given a certain situation, should that be called smart? Is that a desirable property? And I don't think like the answer is super clear cut here, because as the authors mentioned in this paper, humans do this as well to an extent, right? Like muscle memory is exactly this. I've encountered the exact same situation. I don't need to do any cognitive lifting. I just perform the exact same action. So this is a component to intelligence, but if it turns out that this is the only thing that reinforcement learning is good for, then I think there's a good, strong argument for it not being sufficient for like just general artificial intelligence. Let me see what else is there. Okay, could you repeat your question, please? Because I think it's quite interesting.
My question?
Yeah.
So no, my main question was the last section was basically sounded like the authors were talking about how we could report more about the robustness of the algorithms and about their performances overall, but about actually addressing the problem of these algorithms not being robust. How might we go about doing that?
Yeah. So
I like your previous answer, by the way.
Yeah. Just to summarize, I have not seen a very good way of doing that yet. There have been some attempts in trying to manipulate the environment in which the agent lives, but it's sort of like a game of cat and mouse where the researchers introduce additional restrictions for the algorithm, and the algorithm still is able to circumvent those restrictions and memorize things apart from that. So that may or may, like an appropriate setting of things may or may not turn out to be feasible, but so far we haven't found anything. Cool. All right. Let me just see if there's anything else that I want to mention before we go into a discussion. Yeah, so this from another paper. There's this suggestion which I quite liked, is we have the capacity to provide, let's say, containers that can replicate experiments exactly. As we see that with deep reinforcement learning, things can be so brittle that just based on a description, no matter how good the description is, it could be impossible to reproduce results. I think that an argument can be made that paper is incomplete unless the exact implementation that can be run by somebody else and produce the exact same results is provided. This is actually quite interesting because we're seeing this trend, especially from places like OpenAI, of just releasing technical reports without backing of even like reference implementation for some of these things. Yeah, we've seen that you cannot validate the results that they provide just based on that technical report. Cool. All right. So yeah, I think these are all the points that I wanted to bring. This has mostly been like just flagging up different issues here. So I'm wondering whether people had any thoughts, like no matter how simplistic they may seem, on what could be done, what could be done here.
I agree with you.
Yeah.
I think it is a good idea to have this one cohesive thing, on the caveat that we do not encourage all of the testing to be on optimizing the performance in this one for the reason of us ignoring all of the possibilities of having these inconsistent performances, like we've already discussed in the paper.
Yeah, so that's a very good point. Is like, how do you do that in a way that does not then make comparison dependent only on the results provided by somebody else in a previous paper, right? We have that tendency in regular machine learning of focusing on, sometimes even synthetic data sets and focusing solely on this. Reinforcement learning has the advantage of, focusing on distribution over data sets. So how do we utilize that in a way that's both fair for comparison across the different architectures, but also does not focus on a single row or like a single subset of those from that distribution. Cool. All right. Any thoughts or like comments on the overall situation? Cool. Doesn't seem so. All right. Yeah, I'm gonna wrap up then. I'm gonna leave it to you, Sakina, to mention if there's anything.
Yeah, thank you so much. That was really, really good. You're able to explain the paper in a much better way than I could read it myself. So thank you a lot. Yeah, if there's no more questions, then I'll end the recording, and thank you everyone for coming.
Thanks so much,